Hello everyone, my name is Nadav Barak from Ben-Gurion University. Today I'm going to share with you a short review of a joint work with Sivan Sabato, approximating a distribution using weight curves. Imagine the following scenario. You are a researcher with full access to a big hospital patient records and wish to create a classifier for a different hospital with a different patient distribution. In the target hospital, the situation is quite different. You have no direct access to the patient records, no random sample, and the only access is via aggregated counting queries on the database. For example, a counting query could retrieve the percentage of patients whose age is above 50, weight between 40 and 90 kilograms, and resting heart rate below 180. And so our question is, can we perform learning tasks under this setting? Let's formalize the problem. Our input is a dataset of domain example. We have no random sample from the target distribution, and the only access to it is via weight queries. In the case of the medical records, the weight query is represented by a database counting query. In general, the weight query retrieves the probability of a certain subset of the domain according to the target distribution. Our goal is reweighting the dataset to match the target distribution. The reweighted dataset can then be used for various machine learning tasks. We formalize the availability of the weight queries by assuming an additional input, a binary tree over the dataset example. Each node in the input tree represents a queryable subset of the domain. Assume x1 to 4 is our dataset. In the figure below, you can see the subset of the domain corresponding to each of those nodes. Similarly, a pruning of the input tree induces a partition of the domain. Our notion of pruning refers to a set of nodes in the tree such that each leaf is descended from exactly one among the set, as can be seen in the figure below. The quality of the input tree will greatly affect our algorithm performance. Our main result is a new active querying algorithm for reweighting the source dataset to approximate the target distribution. AWP finds a small pruning that defines a reweighting of the source dataset. The theoretical guarantees are based upon an additional integer input k that marks the pruning size to be found. We prove in the theorem guarantees on AWP output reweighting and the number of weight queries it requests. So how does it work? We define a new quantity called discrepancy that measures the weight mismatch on a subset of the domain. AWP uses adaptive sampling of weight queries and a new discrepancy estimator. We show in our paper that naive estimators for this quantity fail and prove concentration bounds for the new estimators that we believe is of independent interest. AWP runs an iterative top-down procedure to achieve a low discrepancy pruning of the input tree. The iterative procedure starts with the root node. In the first phase, we select a node in the current pruning and query the weight of a random example underneath it. This is repeated until identifying a relevant node to be split. This phase execution takes inspiration from the upper confidence bound approach common in multi-arms bandit problems. In the second phase, the node found is replaced with the children. This increases the pruning size by 1. Both phases are repeated until a stopping criteria is reached. We report experiments which compare AWP to natural baseline for a variety of scenarios. Some of them resemble the medical records example shown before. Shown here are the results for some of the experiments performed. The Y column represents the normalized L1 distance between the reweighting achieved by the different algorithms and the true weights in the target distribution. In all experiments, except for a single configuration, AWP performs better than the other algorithms. So a quick summary. We have a novel setting in which weight queries are the only access to the target distribution. AWP finds a reweighting of the dataset by finding a suitable pruning. We have theoretical guarantees for the quality of the output reweighting and the number of weight queries. And we have experiments that demonstrate the success of AWP. We encourage you to check out the full paper and contact me or Sivan for any further question you might have regarding this work. Thank you.